My name is Przemyslaw Strzelczak. I represent 9lives Data, and I'll be talking about concurrent deletion in a distributed content-addressable storage system with global deduplication. Before I start, let me just say something about the company I represent. I come from Poland. The 9lives Data is a small R&D company based in Warsaw, and our main project is HydroStore, which is a backend for NEC. HydroStore is a scalable, content-addressable backup storage that features global deduplication. It's owned by NEC. It's on sale on US and Japan, but has been started by 9lives Data founder Cezary Dubnicki in Princeton, New Jersey. Cezary is sitting over there, so you can talk to him offline. And the deletion algorithm I'll be talking about has been implemented in HydroStore, and which has been found as fastest and largest deduplication backup system according to independent Curtis W. Preston analysis in late 2010. Secondary storage systems have to offer large capacity due to duplication, high performance, and high reliability. And in particular, they have to offer data deletion. You can think that data deletion is everywhere, but we found it surprisingly challenging in such systems. This is the plan of my talk. First, I'll summarize requirements and challenges on deletion in distributed cache systems. Then I'll present the deletion algorithm for a cache system with the following assumptions: that it will incur a read-only period, and it will be for the algorithm for centralized systems. And then I will extend this algorithm to support writes with deduplication enabled, and then I will extend it to distributed systems. At the end, I'll talk about implementation in HydroStore. The key requirements for deletion algorithm in secondary storage systems have to somehow be compatible to features of such systems, because those systems have to be continuously available. No read-only period is accepted. Deletion algorithm has to be failure tolerant. Deduplication cannot be disabled during deletion, because otherwise we would end up with increased storage consumptions, and the deletion cannot incur severe impact on user operations, such as backup, restore, or replication. And last key requirement is that deletion impact has to be independent from system size. Let me summarize the data model we assumed. The backup file system consisting, in this example, consisting of 2 files, maps into 4 blocks that come from the chunking of these 2 files. Then such blocks are immutable and content addressable, and they are written to this new blocks are written sequentially, so you can think of it as a log structure kind of system. Then there are also blocks that point to other blocks. So pointers are made explicit in storage. And there are special type of blocks. There are named blocks, which are read through a user-provided key. And there are 2 types of those blocks. Ones are retention roots, which mean tree preservations, and deletion roots that mean that this tree should be deleted. And you can see that file system backups are represented as the trees of blocks built bottom up. We do not deliver the operation to delete single block just because of deduplication. And let me use a working example of how the file system backups are stored in the storage system, you can see that the file blocks are just appended to storage system. Then these two blocks are pointed by a regular block with pointers. Then the next file is also stored. Again, the block with pointers is written, and to mark preservation of those blocks, the retention root pointing to all the structure is written. Then, when the file system is changed, the backup changes, and it's written again. File 1 contains first block, which is unchanged. That's why it ends up as a duplicate. It's resolved by the system as duplicate. But then the second block changes, and it has to be written again. I mean, for the first time, it's seen by the system for the first time. So it's written as new. Then blocks with pointers is written. And to show that the address of the block A is returned, we just redirect the arrow. Then the file 2 is completely unchanged, so the system resolves the complete file as duplicate. We also deduplicate blocks with pointers. And then we write a root of the second backup. Also, we redirect the arrow to show that the block of address of a already existing block is returned. Then we can delete file systems by writing deletion root as mentioned before. Then user can try to write a next backup, and just to for the purpose of next slides, let's assume for a moment that the client failed during writing a third backup. And in this example, I want to show which blocks should be preserved by any deletion algorithm and which blocks should be deleted. Red blocks should be deleted, and green blocks should be preserved. This is what we expect from deletion algorithm to do in such model. Let me now talk about challenges for deletion in content-addressable systems. Again, using the similar, like the same example, with this difference that we assume that third backup is started, but this time it's continued. The writing is continued, but the client doesn't fail, and the file system contains only one file, which is changed to contain only one file that contains blocks F and B only. And let's assume that any deletion algorithm starts, which is marked by this red vertical line, and the red rectangle will illustrate the progress of deletion. Then the algorithm starts to mark alive blocks, but the existing block B is written and is resolved as duplicate. Then the client manages to finish the third backup, but concurrently, deletion algorithm is about to finish marking alive blocks and dead blocks. What we end up is that we actually that any deletion algorithm that cares on just data written before deletion starts, when deletion ends up, we have the situation when alive blocks are in fact deleted, and these are two distinct cases. First is that the dead block has been made alive through deduplication during deletion, and the second block has been made alive by just inserting its address into blocks with pointers. Now I'll go into the base deletion algorithm in centralized system that will be based on deferred reference counting, and the major design decision is that it will be incremental. No whole file systems, not all blocks will be traversed during deletion. here we will just put in a constraint that no writes are allowed during deletion. We will take off this constraint later. This deletion will be organized in two phases, garbage identification and space reclamation. We will focus on the first one only. The second is rather straightforward. And the execution of garbage identification will be done periodically, and its single execution will be called deletion run, started on demand. And in this reference counting, we'll use two versions of counters. One is effective one used by the system, and the second is temporary. Effective is used for reads and writes, and temporary are used for ongoing computation and become effective when deletion run ends. I'll just show how the algorithm works again in the same similar example. We've got the first backup, and on the right we assign a special value of counter to every block. It is called initial zero. You can think of it as not computed yet. Then when deletion run starts, it finds that every block is alive. Nothing is deleted. And it happens in incrementation subphase. Deletion run ends, nothing is deleted. Then client writes next bunch of blocks, the second backup. Then let's assume that it deletes the previous backup, and the third backup is started. In this example, I will show also why this algorithm fails to address the challenges I mentioned before. That the algorithm itself, this base algorithm, works fine when there are new writes, when there are no new writes during deletion. But I will assume that these writes are allowed, and I will show what problems it causes. So this block F comes from the third backup. Then the second deletion execution starts. Incrementation phase bumps counters of blocks shown in the circles. Then, in this scenario, block B is deduplicated. The third backup continues. Then it's the whole backup is finished. But then in a recursive decrementation, some counters decrease, and in particular, some values of counters fall to 0. And the space algorithm, although it works fine when there are no new writes during deletion, if there are any writes, and if there are writes during deletion, it just, as I said, fails to address the challenges mentioned before. How to modify the algorithm to support new writes with the application enabled? First, I will focus how to support new writes during deletion. The algorithm, if a block is completely new, like not seen before, not deduplicated, it's just unconditionally preserved. But there is a problem with the blocks that are written before deletion starts, but they are pointed by blocks somehow not taken into account, written after deletion starts. So the goal will be to preserve such blocks. But the problem is the client can potentially write a pointer to any block written earlier. So somehow we need to work it out. For this, we'll introduce a discrete time based on global counter called epoch. And epoch can be incremented through the operation called advance. And we bind deletion start with the first advance, and the second synchronization point will be somewhere inside deletion. So every deletion advances the epoch twice. And we Further on, every time a user operation finishes, we stamp a returned addresses returned by this operation with some epoch. And we introduce two essential rules. First rule is that in epoch t+2, client is allowed to keep addresses with epoch t+1 and t+2, which means current and or previous one, not older than. And the second restriction is that system can advance to epoch t+2 only if client confirms disposal of addresses from epoch t. So this is kind of twofold agreement, this kind of contract. And I will not recall all the rules about epoch's assignment, just focus on two essential ones. So when non-duplicate block is written in epoch t, it gets epoch t assigned. And we have minimum rule which says that address of block with pointers gets assigned the lowest epoch of addresses inserted. So in this example, even if the block of pointers was written in epoch t+1, it gets epoch t assigned. This rule is essential to force client to somehow flush its addresses, the old addresses. So we require a client to write a temporary retention route to mark preservation of these addresses and then read them to continue regular tree building. To make the algorithm compatible to epochs, and preserve blocks like the G block, we have to do incrementation from blocks between first and second advance, which resolves the problem of deletion blocks written before deletion starts and pointed from newer blocks. Since a system rejects writes of blocks with addresses that have illegal epoch, we can keep track of all references to blocks written before deletion starts. To support deduplication during deletion, what we do, we write as special undelete marker. We mark every block that was used as a base block for deduplication as not deletable during this deletion run. And these undelete markers are kept as bitmaps in RAM, not to impact deduplication much. And in this example, client completes writing some different file system that has the block L shared, and even though block L gets the counter computed to 0, in so-called undeletion subphase, what we do, we restore the counter of block L into initial 0. So we undelete this block. So we don't let the deletion, even if it ends, we don't let deletion to delete this marker. You can have an impression that this scheme is quite straightforward, but you can find details in paper that it is not so easy. Two examples of complications are, for example, how to write deduplication, how to handle deduplication during undeletion, or how to handle deduplication of blocks with pointers and what complication it brings. As I said in my agenda, deletion is, the algorithm is suitable for distributed architecture too, but distributed architecture brings new challenges. And we make only one assumption, that block data is distributed, it's not in one physical location. And the challenges are like the dynamic configuration, nodes can be added, deleted, So the deletion algorithm has to preserve or remove blocks and their parts in consistent manner. The algorithm has to handle failures. Detached nodes can have obsolete counters, and also we have to continue on failure on some nodes. I will not go into how we do it exactly in this presentation. You can find details in papers. Let me recall just key techniques how we support distribution. To continue on failure of some nodes, we compute counters in a redundant manner, and also we introduce a redundancy of undelete markers. They are distributed too. And to recognize obsolete counters, we stamp counters with epochs. And these epochs are refreshed when deletion ends, so that detached nodes get their counters invalidated implicitly. Let's talk about implementation of Hydra store, which has configurable resource division, which means that we can assign that some percentage is assigned to deletion and some percentage is assigned to user operations. The default is 30 versus 70%, and we also tried a minimal, which is less than 1% for deletion, to see what's the impact of undelete markers processing. Experiment used the equipment as shown on the slide, and what we measured is bandwidth of reads and writes during deletion and the deletion duration. The first plot shows the measured impact of garbage identification on writes, and the second bar shows that in 30% deletion share is obeyed, and the third bar shows that undelete markers incur little impact on user operations. The white bar is the base one, which means the write bandwidth with the deduplication ratio varied when no deletion is in progress. The second plot, what we experimented as scalability feature of our algorithm. What we did, we scaled the number of nodes from 4 to 16, and we also scaled the amount of data proportionally, and we performed 4 similar experiments and measured corresponding durations of deletion processes. And as you can see, deletion duration remains almost constant. Conclusions are that I've showed a solution for a problem of deletion in distributed CAS systems. The algorithm features support for writing with deduplication enabled during deletion, and features it's failure tolerant and it's scalable. And key techniques we used are epochs and undelete markers. And I also show implementation in Hydra store that incurs little performance impact. Thank you very much. I'm ready to answer questions.
Fabian, BRS EMC. So what's the size of your block, average size, and the size of the identifier that you use for the duplication?
The average, in particular, in Hydra store deployment, the chunk size is 64 kilobytes. So, and the block address, I believe, is 20 bytes or so.
Okay, so during the bitmap tracking, during the deletion operation, how do you map 20 bytes to a single bit in memory?
How can I map it?
Yes.
Our deduplication operation already gives me the container ID and a logical offset in the container.
Mm-hmm.
So I can just...
Okay, I see. Okay, thanks.
Mark Lillibridge from HP Labs. So you put an undelete marker on blocks that are being referred to by things being written in the during the deletion.
Can you
Sorry.
Speak a little bit louder?
The mic's a little tricky. You put an undelete marker on a block that was already existing but is being pointed to by a new block with pointers that's being written during the deletion. And then you set its counter to I0, is that correct?
Yes.
How do you figure out what the correct count should be later?
If it's 0, it's restored into I0, right? We mean...
Suppose the block already had a count of 5.
Yes.
And we add another pointer to it.
Yes.
But we don't put 6, we just put I0. How do we get 6?
This restoration, it just works. I mean, it's done for blocks that are going to be deleted. If it's a positive counter, the undelete marker doesn't do anything.
I got you now. Thank you.